we looked at Newton's laws of motion. We looked at the general equation F equals ma. We also looked at Newton's third law of motion. So in this lesson, we are going to look at momentum and collision. We shall be able to define what is meant by momentum. We shall state the principle of conservation of linear momentum. We shall derive the principle of linear momentum conservation given two bodies moving along the same line. We shall also look at several examples of calculations that require you to use this knowledge of linear momentum conservation. Then we shall later look at collisions. We shall begin by the definition of a collision. And lastly, we shall look at the three types of collision: the perfectly elastic, inelastic, and perfectly inelastic collision. So you will be able to define or to distinguish or to state the differences between those three types of collisions. So let's begin with the first item on the menu, and that is defining what is meant by momentum. Question: momentum. So we shall be defining momentum as a product of mass and its velocity. So momentum, it's the product of mass and its velocity. Mathematically, if we use letter P for momentum, then we shall be able to use the given formula, where P is the momentum, M is the mass, and V is the velocity. Mass is measured in kilograms, V is measured in meters per second, and therefore P will have a unit of kilograms, meters per second. Remember, units are equally important in physics. Principle of conservation of linear momentum. Principle of conservation of linear momentum. Now, when two bodies collide, there is always a transfer of momentum and energy. One body loses the energy while conservation of linear momentum. So when two bodies interact, for example, in a collision, it could be like an accident or a ball that has been kicked, there is always a transfer of momentum from one system to another. So the principle states that in any interaction, the sum of momentum before impact is equal to the sum of momentum after impact, provided no external force acts on the system of colliding bodies, on the system of the colliding bodies. So this statement is so important when it comes to calculations and also when it comes in distinguishing the various types of collisions as we are going to see them. It is a common question for you to be asked to prove the given principle. Question. So given two bodies of mass m1 and m2 moving at speeds u1 and u2 respectively, along a straight line, in the same direction, if the two bodies collide and move with the speed v1 and v2 respectively, Roman 1, state the condition for the collision to occur. Roman 2, prove that momentum is conserved. So given two bodies of mass m1 and m2 moving at speed u1 and u2 respectively along a straight line in the same direction, if the two bodies collide and move with speed v1 and v2 respectively after collision, Roman 1, state the condition for the collision to occur. Roman 2, prove that momentum is conserved. Roman 1. So I'm going to use spheres to represent my two bodies. So if this is my body 1 of mass m1 and I happen to have another body of mass m2, so for consistency let this be moving at that speed and also let m2 be moving at speed u2. Then after impact, these two bodies, so this is mass m1 and this is of mass m2. This one moves with velocity v1 and also this one moves with velocity v2, ignoring friction. Remember, in our definition we say that the momentum is conserved provided no external force acts on the system of the colliding bodies. Now Roman 1 requires us to state the condition for the collision to occur. So in this case, for collision to result, mass M1 should be moving at a speed greater than that of M2. So Roman 1, so mass M1 should be moving at a speed greater than that of M2 before impact. Before impact. Then after impact, so if this is after impact, M2 should move at a speed greater than that of M1. Otherwise, these two bodies would collide for the second time, which is practically impossible. So after impact, so I'm going to be brief, V2 is greater than V1, and we are assuming that these bodies continue to move along the same line. So that is the condition. If V2 is less than V1, then these two bodies will collide again. So for this case, we are assuming that the two bodies don't stick after impact. They continue moving, but with different velocities. We are now going to look at Roman 2, which requires us to prove that momentum is conserved. So this is my body. So this is after you've seen that this is V2, M2, M1, V1. This is M2, V2, M1. One, this is before impact. This is after impact. So now during impact, so mass M1 exerts a force which I'm going to call F12 onto mass M2. So that's one fact. So also mass M2 exerts a force which I'm going to call F21 onto mass M1. From Newton's third law of motion, from Newton's third law, F12 must be equal to negative F21. So I'm going to call this my first equation. So this is a statement obtained from Newton's third law. Now if the collision or the interaction, if the collision lasts for time t, So F12, that is the force experienced by M1, is equal to MA, and in this case A is V1 minus U1 divided by T. Similarly, F21, M2, V2 minus U2 divided by T. So I can call those couple of equations equation 2. Now I'm going to substitute the values of F12 and F21 in equation 1. So combining equation 1 and 2, combining equation 1, we shall have, where there is F12, M1 V1 minus U1 out of T is equal to M2 negative into V2 minus U2 divided by T. Since it is the same, the 2 will cancel. So we shall have M1 V1 minus M1 U1 is equal to negative M2 V2 plus M2 U2. So when I try to rearrange the equation, we shall get M1 V1 plus M2 V2 is equal to M1 U1 plus M2 U2. All M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. Now this is actually the sum of momentum before collision. So this is sum of momentum before collision, and this is equal to sum of momentum after collision. So we have proved the principle of conservation of linear momentum. The sum of momentum before collision is equal to the sum of momentum after collision, provided we don't have any external force acting on the bodies. All the mathematical expression for conservation of linear momentum. All along in the terms we've been using, we have been mentioning the term collision. However, if you were asked to define what is meant by a collision, it would be unfortunate you leaving the space blank. So it is important actually to understand the terms. Now, how do you define a collision? So we define a collision. So a collision, it's an interaction. It's an interaction between bodies that involve the transfer of momentum and kinetic energy. In any collision, energy is conserved. So when we are still in O level, you may have looked at the principle of conservation of energy, which stated that energy can neither be created nor destroyed, but it's just transformed from one state, or it's just changed from one state to another. Likewise, if two bodies interact or collide, we may hear the sound, we may see the light. All those are forms of energy. So when you sum them up, the energy remains constant. However, basically we are going to look at kinetic energy and the momentum in defining the various types of collision. So in mechanics we are going to look at namely 3 types of collision. So we have 3 types of collisions. Types of collision. There is what we call the perfectly elastic or elastic collision. Perfectly elastic, or can also call it elastic collision. There is the inelastic collision. And the third one is the perfectly inelastic collision. The good news is that in all these types of collision, linear momentum is conserved. However, kinetic energy is not conserved in the second and third type of collision. So collision is the type of collision in which linear momentum and kinetic energy of the bodies is conserved, and the bodies move with different velocities after impact. Perfectly elastic collision, one, it's the kind of collision in which momentum and kinetic energy is conserved, and the bodies move with the different velocities after impact, i.e. they don't stick together. Example, two bodies of mass m1 and m2 are moving at speed u1 and u2 respectively along a straight line, but in opposite so after impact, the two bodies move with the speeds collision is perfectly elastic, or if the collision is elastic, Roman 1, write down the equation of linear momentum conservation. Roman 2, write down the equation of kinetic energy conservation. Write down the equation of kinetic energy conservation. Two bodies of mass m1 and m2 moving at speed given respectively along a straight line but in opposite direction. After impact, the two bodies move with speeds v1 and v2. If the collision is elastic, write down the equation of linear momentum conservation. And Roman 2, write down the equation of kinetic energy conservation. 1, speed u1, and have body m2 moving at speed u2. So after impact, so we have linear will be there. So after they bang, one may bounce back and one may continue moving. So if this one moves with the velocity v1, so we can have our m2 moving with the velocity v2. So Roman 1 requires us to write down the statement or the equation of linear momentum conservation. So for simplicity, since these bodies are moving along the same straight line, we shall have m1 u1. Now, since u2 is moving in the opposite direction, a negative sign will cater for it. This negative is as a result of u2 being negative. So this will equal to m1 v1 plus m2 v2. Then Roman 2, if the collision is perfectly elastic, the sum of kinetic energy before collision must be the same. Kinetic energy cannot be negative because of the v squared. So even if the velocity is negative, once it is squared, it turns out to be positive. So we shall have a half m1 u1 squared plus a half m2 u2 squared must be equal to a half m1 v1 squared plus a half m2 v2 squared. So these are the two basic equations for a perfectly elastic collision. Actually, we are having two equations and we are having four unknowns. So if two of the unknowns are given with these two simultaneous equations, if the mass is unknown, you can calculate the other. So you just have to apply some simple mathematics. Of mass 5 kilograms is moving with the velocity of 2.0 meters per second to the right. It collides with the body of mass 3 kilograms moving with a velocity of 2.0 meters per second to the left. If the collision is a head-on elastic collision, determine the velocity of the two bodies after collision. So if you are given such a challenge, sketching it will just ease your working. So a body. So we are going just to use spheres to represent our system of colliding bodies. So if this is of mass m1 moving to the right, it collides with a body of mass that moving to the left. So you have to understand the question, otherwise if you fail to interpret it, chances of you getting it wrong are high. Now after impact, I'm not certain in which direction the bodies will move. However, I'm going to suggest that let this move with velocity v1, and maybe also let this to move with velocity v2. So this is my m2, this is my m1. So the calculations will bring it out. For example, if I get v1 as a negative, then that will mean that the direction which I originally assumed was the opposite. So M1 is given as 5.0 kilograms. So U1 is equal to 2 meters per second. M2 is 3 kilograms. M2 is 3 kilograms. Moving with velocity V2 is V2, taking the magnitude of the speed is 2.0 meters per second. So if the collision is perfectly elastic, determine the velocities of the two bodies after collision. So the question requires us to find V1 and also to find V2, meaning that we have to solve two simultaneous equations. So we shall begin with the principle of conservation of linear momentum. So from conservation of linear momentum, so we shall have our M1 U1 minus M2 U2 equals M1 V1 plus M2 V2. So you can call this our first equation. Then from kinetic energy conservation, energy conservation, shall have a half M1 U1 squared plus a half M2 U2 squared is equal to a half M1 V1 squared plus a half M2 V2 squared. So I can call this my second equation. Now these equations can be simplified further. Since we are interested in V1 and V2, you may be tempted to make V1 the subject using equation 1 and you substitute it in equation 2. Fine, it may work, but it will give you an equation that is hard to solve. Actually, it will be a quadratic equation. The good news is that you can find, or you can combine these two equations to form another third equation which is linear, that is having no powers on the unknowns. Then later you will solve it with the first one, and that is the approach which we are going to use. Actually, if you are solving such a kind of simultaneous equations, you'll find ways of first combining the two to obtain a simple linear equation. So from equation 1, from 1 we shall have m1 bracket u1 minus v1 is equal to m2 bracket v2 minus u2. So it's now plus u2. So I have collected like terms and I have factorized it. Remember, always time is on our neck. So from equation 2, I'm going to do the same. The halves will disappear, they will cancel, so you shall get m1 u1 squared minus v1 squared is equal to m2 into v2 squared minus u2 squared. Now I'm going to divide these two equations. So 1 divided by 2, so we shall have our m1 bracket u1 minus v1 divided by m1. So this is the same as u1 using the knowledge of difference of two squares, v1 into u1 minus v1 is equal to m2 bracket v2 plus u2, the whole of this over m2, again using the knowledge of difference of two squares, get v2 minus u2. Now this u1 minus v1 will disappear, even this m2, and when we rearrange the equation, so we shall get u1 plus v1 is equal to v2 minus u2. So I'm going to call this my third equation. So I'm going now to solve simultaneously the first equation and the third in order to get the values of v1 and v2. So eliminating v1 from equation 1 and 2, from equation 1 and 3, so I'm going to, this time let me use substitutions. I'm going to make v1 the subject here and I substitute it there. So shall have v1 is equal to v2 minus u2 minus u1. Now from equation 1, the first one, so we shall have our m1 u1 minus m2 u2 is equal to m1, where there is v1 I'll put v2 minus u2 minus u1 plus m2 v2. So now I'm going to make my V2 the subject. M2 U2 M2 U2. So when this process becomes plus M1 U2 is equal to M1 plus M2 V2. So you can simplify this further. You shall get 2 M1 U1. This can be plus bracket M1 minus M2 U2 is equal to M1 plus M2 V2. So our V2 in this case M1 minus M2 U2 divided by M1 plus M2. So you can now substitute. So 2 times M1 5 times U1, which is a 2, plus bracket M1 is a 5 minus M2 is a 3 times U2 so divided by M1 plus M2, 5 plus 3. So using your calculator you will get V2 equals 2 times 5 times 2 plus so this is the same as 24 divided by 8, and therefore 24 divided by V2 is 3 meters per second. So in order to get V1, you substitute back the value of V2. So V1 will equal to, so you go back where I made V1 the subject, V2 minus U2 minus U1. Now my V2 is a 3 minus U a 2 minus U1, which is a 2. And when you simplify this, you get negative 1 meters per second. So V2 is that, V1 is equal to negative 1 meters per second. Now the negative 1 indicates that in reality after impact it will continue moving in this direction. It will bounce back at a speed of 1 meters per second. May be asked to give examples. In life or in reality, is there any interaction which is elastic or perfectly elastic? A simple example is the collision between gas molecules, and actually that is the only interaction that can qualify to be a perfectly elastic. In any interaction where you hear sound, then that would mean that some energy is being changed into sound. Now let's look at the second type of collision, and that is inelastic So inelastic collision, by definition, it's the kind of collision, or it's the type of collision in which momentum is conserved, kinetic energy is not conserved, kinetic energy is not conserved, and bodies don't stick together after impact, and bodies do not stick together after impact. In most cases, the bodies after impact will move in opposite, or will move in different directions. They will not continue moving along the same straight line. An example, if you have ever played ball, so once the cube ball strikes, other balls, they will move in different directions. So that is an example of an inelastic collision. When a ball, or when you hit a golf ball, on a microscopic scale, that golf ball will deform, although you may not see it, but it will also be an example of an inelastic collision. Basically, we shall be looking at the first and the last. That is the perfectly inelastic. Perfectly inelastic. So it's the type of collision or impact. It's the type of collision in which momentum is conserved, kinetic energy is not conserved, kinetic energy is not conserved, and the bodies stick and move together. Bodies stick and move together after impact or collision. An example, an arrow fired in a wooden block. If the two after impact stick and move as a whole, that would be an example of perfectly inelastic collision. So what is important? That bodies move together with a common velocity. So let's try to look at a simple example which requires us to mass 600 kilograms traveling at 20 meters per second collides with a stationary truck of mass 1,400 kilograms. Full stop. The two cars are locked together after collision. Find Roman 1, the common velocity of the cars. Roman 2, the loss of kinetic energy. So in this case, when they say they are locked together, you knew that the collision was perfectly elastic. So it was perfectly inelastic. So originally, we are having this one is moving that at rest. The two, they lock together. They will move with a common velocity which I'm going to be. So this is M2, M1. M1, M2 over M1, M2 before impact. This is after impact. So we are given that M1 is equal to 1600 kilograms and U1 is equal to 20 meters per second. 20 meters per second. So M2 is equal to 1400 kilograms. So from the term, from the principle of linear momentum conservation, so we shall have our M1, U1, this is at rest, M1 plus M2 V. Therefore, our V is equal to M1 U1 over M1 plus M2. And when we substitute, so this is the ratio, even if the masses it's supposed to have the same units, 600 times U1, which is 20, divided by 600 plus 1400. So do it equal to 6 times 2, that is 12, 1, 2, 3, divided by 2000. 1, 2, 3. So this is 60 meters per second. So V. So that's the common velocity with which the interlocked cars will move. So that is Roman 1. Roman 2, calculating the loss of kinetic energy. Call it KL. So in this case, the kinetic energy before impact is greater than that after impact. So we shall have KL will equal to a half M1 U1 squared minus a half M1 plus M2V squared. And when you substitute, times 600 times 20 squared minus half times squared. So when you simplify, shall get 300 times 20 squared. So that would be the loss in kinetic energy, 84,000 joules. It will require you to have both the knowledge of a perfectly elastic and perfectly inelastic collision. So it combines the two. Balls A, B, and C of masses M1 and M2 and M3 respectively lie on a straight line on a smooth surface. The balls are initially at rest. Ball A is projected with the velocity v1 towards B and makes an elastic collision with B. If B moves and makes a perfectly inelastic collision with C, show that both B and C move with a velocity given in that expression. B and C. Of masses M1, M2, M3 respectively. The balls are initially at rest. Ball A is projected with the velocity v1, is projected with the velocity v1 towards B. So if B moves and makes an inelastic collision, so it means that after impact, so B is going to move with a velocity which I'm going to call maybe, so since they have used the V1, there is no harm if I use U. So let U2 be the speed of M2 after impact. Likewise, we shall also have let U1 be the speed of M1 after impact. So if the equation is perfectly, if the collision or the interaction is perfectly elastic or elastic, then from linear momentum conservation, we shall have M1 V1 is equal to M1 U1 plus M2 U2. Similarly, from kinetic energy conservation, so we shall have a half M1 V1 squared being equal to a half M1 U1 squared plus a half M2 U2 squared. So let me call this my second equation. Now if M2 collides with the M3, remember M2 will be moving with the speed U2. So collision, so if M collides with the M3 and we are told that the collision is perfectly inelastic, it means both will move with the same velocity since they will stick together. So from momentum conservation, we shall have M2 U2 will equal to M2 plus M3 into V, where V will be the speed with which actually it's what is called the V3. So this is now my third equation. Now they want us to derive or to show the given expression, meaning that I have the value of U2 in terms of M1, M2 and V1. So that is the task. So I'm going to combine these two equations so that I eliminate the U1. So the equation I make U2 the subject, and then I will substitute for U2 in this third equation. So I'm going to eliminate U1 from Roman 1 and 2. However, this second equation, since it has got these squared terms, I'm going to first combine the two to obtain a third equation which is a bit friendly. That's where we are heading to. You are expected to have a plan. So eliminating U1 and 2, so we shall have M1. So from 1 we shall have M1 bracket V1 minus U1 is equal to M2 U2. From equation 2, we shall have again the halves are going to disappear. M1 bracket V1 squared minus U1 squared equals the halves M2 U2 squared. So I'm going to divide these two. So 1 divided by 2, the M1s will go, so we shall have V1 minus U1 divided by, so this is the difference of two squares, V1 plus U1, V1 minus U1 is equal to the M2 will go, so it's going to be 1 over U2. So this U2 will cancel with one of the squares. So this one will also vanish with that. And therefore we shall have our U2 being equal to V1 plus U1. So I'm going to make U1 the subject and I substitute it U1 the subject. We shall get our U1 is equal to U2 minus V1. Now we are going to substitute the value of U1 in equation 1. So our equation 1 is now going to become M1 V1 is equal to M1, where there is U1, put U2 minus V1 plus M2 U2. So when you try to make U2 the subject, M1 V1 is equal to M1 U2 minus M1 V1 plus M2 U2. So bring this side, so shall get twice M1 V1 being equal to M1 plus M2 into U2. So you get your U2 is equal to this m1 v1 bracket m1 plus m2. So after getting the value of u2, so I can call this to be my fourth equation. So I'm going to eliminate u2 from the third equation and the fourth one. I believe we shall get what is required. From equation 3 and 4, so you shall get, so where there is u2, 2 m1 v1 divided by 2m1 m1 plus m2 m1 plus m2 equals m2 plus m3 into v3. When you make v3 the subject, you get your v3 equals to m1 to v1 divided by m1 plus m2 plus m3. And when you compare this with what was given, we shall have proved the expression, and that will mark the end of your working. Actually requires you to have the knowledge of momentum conservation and a bit of projectiles. So a bullet of mass 4 grams moving horizontally at a speed of 200 meters per second strikes a wooden block of mass 4 kilograms resting at the edge of a table. The bullet gets embedded into the block and the two fall at a distance of 6 meters from the foot of the table as shown in the figure. Calculate the height of the table. So this is going to be our height h. So let's look at the solution. To let v be the velocity of the composite after impact. So let v of the composite after impact. So again, let t be the time taken for the composite to fall through vertical height h. So in this case, after impact, when this body is moving in space, we are going to handle it as a body projected horizontally. So when you consider the horizontal motion, so for horizontal motion, we shall have our 60 is equal to Vt. That is equation 1. Now for vertical motion, we shall have our h being equal to 0 plus half g t squared So eliminating t from these two equations, we shall have our h is equal to half g. Now where there is t, we are going to put 6 divided by v, this bracket, squared. So t is 6 divided by v. Actually this is the same as g out of 2 times 36 divided by v squared. So you can even simplify this further. 36 divided by 2. This is 18g v squared. Now what is preventing us from getting the value of h is that we don't have the value of v. So in order to get the value of v, we are going to apply the knowledge of momentum conservation. So from linear momentum conservation, so if our bullet is of mass 4 grams, we are going to convert the grams to kilograms by dividing. So this would be the mass times the velocity with which it is moving, 200 meters per second, plus 0, since the other block was at rest, will equal to the mass of the composite plus that of the wooden block is given as 4 kilograms times v. So we are having now task of finding the value of v. So this is the same as 4 times 2 is 800 divided by 1000 is equal to, this is going to be 4000, 4004 divided by 1000 v. So this 1000 will cancel. So we shall get our v is equal to 800 divided by 4,004. So meters per second. So after getting the value of v, therefore our height, which is h, will equal to h will be equal to 18 times 9.81 divided by v squared. So 800 divided by 4004 squared. So I am getting, after squaring, 0.0399. Therefore my h equals 18 times 9.81 divided by answer. So we are getting 423.3 meters.